Hi everyone, and welcome to part 3 of a multi-part series where I'll be going through how to enter input data and results in the RF-DYNAM Pro design module. In this part, I'm showing you how to enter the input data needed to run an RSA. If you missed parts 1 and 2, I recommend going back and watching these because those steps in those videos are required for running a response spectrum analysis. So I will link parts 1 and 2 down below in the description. But for now, let's get started. So since in the previous videos, we have already determined the natural behavior of our structure under the applied cases and combinations, we can now move on to an RSA. So you can see these results are shown, and after running about 50 modes shapes, we're reaching at least 90% mass participation in each orthogonal direction. So now we can go back into the RF-DYNAM Pro add-on module. And we can activate the add-on module response spectrum analysis with generation of equivalent loads. So with this, once I activate it, you'll see that at the top here, we will get two new tabs. One is for the response spectra we need to generate based off the standard, and the other one is to generate our dynamic load cases and create our equivalent loads. So let's first go into the response spectra tab. And this is where we want to generate our response spectra, and you can see that we can do this according to a standard. Right now you can see we have a long list of standards. So the first thing we need to do is select the standard we would like to create this or generate this response spectra from. So I'll choose the ASC 716 for this example, but you can choose from any of the other standards as well. So you can also see we have the choice to create these parameters based on user-defined info. So we can choose this option if you would like to just enter your acceleration and period manually, like this. Now we just need to enter our parameters with regards to the location of the structure. And so what we can do is use the GeoZone tool on our website to find these parameters. I already did this, and I assume that the location of this structure is located in Philadelphia, Pennsylvania, in the United States. The ground motion parameters we need to enter here are what we recorded from the GeoZone tool. So we need to enter the site class, and this is determined from the standard. Then we need to enter the response acceleration parameter for short periods, which in our case, for this location, is 20% of g. Then we need to enter the response acceleration period for 1 second periods, which is 6% for this location. And then the last parameter we need to enter is the long period transitional period, t sub l, and for this location is 6 seconds. And then the rest of these parameters can all be or will all be generated automatically. So once we enter those parameters, you'll see down here that our response spectra is created. And we also have this information located in our table tab here, which we can export out to Microsoft Excel if we would like to. So now we can move on to the dynamic load cases tab. So here you'll notice that the only option given to me under this tab is the equivalent static force analysis. And this is because I only activated this dynamic module under the general tab. All of these other options have more to do with other add-on modules like time history, for example. We do also need to solve for our one natural vibrations case, which we have automatically selected here. And then the next thing we need to do is go under the equivalent force analysis tab here to tell the program which directions we would need to excite the structure, for example. For this video, I'm only concerned with the two orthogonal directions x and y, so I will activate those. If I was concerned, again, with vertical seismic, then of course I would activate z as well. The next info we need to enter according to the ASC 716 is the eccentricities for accidental torsion. And how we do this is we set 5% of the structure's dimensions perpendicular to the direction of the applied forces. So if I activate this in the x direction, we just need to choose 5% of the total length in the x direction of the structure. And I already calculated this value, and it came out to be 16.5 5, 6 inches in the x direction, the global x direction. And then now in a similar manner, we need to have the eccentricity in the y, and we can compare that to the direction in the y of the short direction of our structure, and 5% of that dimension is 12 inches. So we can enter that. And now the program's smart enough to know to multiply the forces in the x and y directions to these eccentricities to create our accidental torsion. Now what we need to do is choose the combination rule for our modal responses. This is how the program combines all of the load cases created from the equivalent seismic forces in each direction into an envelope solution. So there's the two options here, the square root sum of the square, or SRSS rule, or the complete quadratic combination rule, or the CQC rule. The main difference between these two rules, just to sum them up quickly, is that the SRSS rule does not take damping into consideration, whereas the CQC rule does take damping into consideration. For this tutorial, we can set the rule to the CQC rule, just so we can see how damping works, and you can then see that this activates the damping tab up at the top here. We then can also activate our load cases over on the right here, so they're already automatically activated, and then we need to also activate our result combinations, which is where the load cases will be combined according to our modal response combination rule. And then lastly, we need to activate the 130 rule according to the ASC 716, telling us that we have to have a result combination that combines 100% of the forces in the x plus 30% of the forces in the y. And then this will also do the reverse and do 100% of the y and 30% of the x forces, creating two result combinations. So then we can move on to the damping tab. And like I said before, if you use the CQC rule, then you have to consider damping, or else there isn't much difference between the CQC and SRSS rules. So in this tab, you can either enter Rayleigh damping coefficients, or we can use the Leer's damping, which is, for example, around maybe 0.02 for a steel structure. So we will just assume this value for this example. Now in the last tab, mode shapes, the program wants to use all calculated eigenvalues to create equivalent loads. This really isn't necessary in this case because we just want to use 90% of the structure's mass participation. So what we can do is, instead of selecting all of our equivalent loads here, we can choose this option, deselect modes with, and we can enter the value 0.005 or 0.5%. And so what this will do is it will deselect all mode shapes that have less than 0.5% mass participation. And this basically will help us with reducing our results and just creating a cleaner analysis. And you can still see here, even with deselecting those modes, that we were meeting our 90% mass participation in both the X and Y directions. So the last thing we need to do now is just hit OK and calculate. And so this is the end of this video, and in the next one, I will go through these results and explain how to view and understand them. So thank you so much for watching, and I will see you in the next one.